All right, excellent. Well, yes, good morning or good afternoon or hello, wherever you are in the world. My name is Joe Reed. I'm a civil engineer here at the National Park Service. We are part of the U.S. Department of the Interior. I'm going to be telling you a little bit about some recent engineering construction that we've done here along the Chesapeake and Ohio Canal in the National Historical Park. Over the next couple of minutes, we'll be going through and I'm going to try to provide a summary of some of the unique engineering aspects of the historic structures that we've encountered over the past couple of years. I'll start with an agency or park overview just in case you guys aren't super familiar with the National Park Service in the United States. We'll go through some of the recently completed work throughout the park, and then we'll end up with one project that's still under construction. So hopping right into it, this is the United States of America. This is showing all 435 individual park units of the National Park Service. The park that I work with exclusively is the C&O Canal National Historical Park, which is on the east side of the United States. And I'll show you a slide on the next page, but it really runs from Washington, D.C., the capital, up to Cumberland, Maryland, 184.5 miles. And really, the whole mission of the National Park Service is to preserve unimpaired the natural and cultural resources and values of the National Park system for the enjoyment, education, and inspiration of this and future generations. So this is the C&O Canal as it is today. The green line is the canal system. It runs on the left bank of the Potomac River that goes all the way from Washington, D.C., down here on the right, up to Cumberland, Maryland. And along the way, it goes 184.5 miles. It's 20,000 acres currently in area. And it was originally a canal system that was broken ground on July 4th, 1828 by John Quincy Adams. And it consisted of 74 lift locks that were created to raise the boats over 605 feet from the journey of DC to Cumberland or the other way, depending on which way the traffic's going. Along the way, they used 11 stone aqueducts, which carry the canal over the major Potomac tributaries, which I'll talk about one later on. They had over 168 historic culverts, which carried the drainage from the adjacent areas underneath the canal to the Potomac River. Multiple waste weirs, which were the water control structures to control the water levels in the canal, an assortment of stop locks, river locks, bridges, shops, lock houses, ancillary structures, and everything it needed to have a canal system to support a canal system that remained in operation from about 1850, which is when they really had the full thing running, because the last piece of the puzzle to complete was the Paw Paw Tunnel, all the way until 1924, where the canal operation really ceased operation after 1924. It didn't become a National Historical Park until 1971, and in fact, 2 years ago, we celebrated our 50th anniversary as a National Historical Park. So even though the whole canal was about 184.5 miles long, all the way along the Green Line, we currently today only have about 33 miles or 18% that is intentionally watered, and of the 33 miles, about 23 miles that are watered really extend from somewhere about here down through Great Falls into Washington, D.C. And it's still fed with the water from the river using gravity and that 1820s area technology. So of the 74 lift locks, only 24 of the locks even still have lock gates. So just to kind of bound the historical nature of the park, and that it's not a fully functioning system, ready for navigation at the drop of a hat. So the last thing I'll leave you with in terms of just the park overview is that we do receive about 5 million visitors every year. In fact, in 2020, it was the 8th most visited unit in the National Park System. And typically we're up in the top 20. In 2021, we were 11th most visited, and in 2022, we were 16th most visited. So not only are we trying to address a lot of the projects to address the deferred maintenance throughout the park, we're also trying to preserve historic structures, and we're also realizing the many additional advantages to providing the interpretation and recreation aspects that tie in well with the National Park Service mission. So this is the first project I'll show you guys about. This is down in Georgetown, Washington, D.C. It's about mile marker 0.5, so it's way down at the downstream end. This is a 1939 image that shows lock number 4. This really goes right through the heart of Washington, D.C. and the canal systems. This is the very end of it. This is 1924 image of lock number 4, or lock number 3. And both of these locks were originally constructed 1829 to 1831, so over 192 years ago. These locks were built, and they were comprised primarily of stone masonry, and that was actually quarried just down the road on Aquia Creek, Stafford County, Virginia, 40 miles away, and they boated in the stones and everything else and built it up from there. And then obviously throughout the 192-year lifespan of the locks, there were successive repairs that were done using different types of geology and bricks and granite and different things like that. Well, one of the primary differences between Lock 4 that you see here and Lock 3 that you see here is the foundations. Lock 4 is actually founded on bedrock, and Lock 3, even though it's just a few hundred feet away, was put on a timber mat, and bedrock was nowhere to be found. That's just the nature of the geology in Washington, D.C. with the fractures and the varying bedrock and everything else. So one of the primary drivers for the work at Lock 3 was that there's actually instability in the locks, and I'll show you some of the sections, different things like that. But they actually found that between 2004 and 2011, they did a couple studies, and they found that these lock walls were not only leaning inward, but they were actually actively leaning inward and getting closer and closer together. So typically, this is a lock that's used for our interpretive boat program, and I'll show you a picture of that on the next page. But there's really a couple of primary goals in this project, and one was to repair a primary park resource. The other was to restore the operations of the interpretive canal boat program, correct some visitor and public safety threats, and then also protect adjacent private property. So to that end, from 2016 to 2019, the physical construction took place, and it really rebuilt lock number 3 from the foundation up. It took all the existing stone that comprised the lock. We tried to salvage as much as possible, and what that entailed was physically going through and numbering each of the face stones, cataloging that, documenting that, and then palletizing it, and then keeping it organized, and then bringing it back and putting it back in the same location. Where we had to, we would supplement or augment those stones that we need to replace with an off-site source that actually came out of Pennsylvania, 200 miles north of the site. We also, would put all the lock back together. We installed some stormwater management features, hardscapes, and then really lock number 4, we did a preservation in place. So total cost of this one was about $7.6 million. This is showing the before, and then this is showing the after with the interpretive canal boat out there. This is the end state of the work that we had at Lock 3 and 4. This is from 2019 after the project was completed, and you can see just where we ended up with Lock 4 here and Lock 3 here. And before I get too far into the presentation, I just wanted to make sure we're using similar terms, so as I say words, people aren't saying, what's a radius wall, or what's a filling port, or things like that. So this is kind of my disclaimer slide. These are the words I'll be using in the context that I'll be using them. So this is just a plan view. So if you're looking down at a lock, this is Lock 3 in particular, down to Lock 4. The water would typically flow from the left to the right. Boats obviously go both directions depending on the path of travel. And what's unique about these first couple locks that the canal company did, and in fact the first 27 locks that they did, was they had internal filling ports. And what that entailed was at the upper end of the lock, so up here, they had a paddle gate, and they could open, and that would allow water to go internal to the lock walls along these filling culverts or ports. And the water would actually come out at the bottom of the lock inside the lock chamber, and it would actually raise the water in the lock from below and minimize those horizontal velocities on those boats and keep them from bumping into the gates and the walls and things like that. So we have those, and we found those during deconstruction. I'll show you some pictures of that. We also have upper lock gates, lower lock gates, the miter sill, and then the miter, which is the physical frame or heavy truss that the lower lock gates and upper lock gates sit on. And all these are timber. We all have timber lock gates today, timber lock gates back then. And even the breast wall right here is really, it's that drop that goes from the upper lock level to the lower lock level. So that's the breast wall right there. So moving on down in here, first thing they did upon construction was whenever they mobilized, they obviously wanted to get the dewatering in, so they had to install cofferdams, and they started getting scaffolding set up. This is what really lock number 3 looked like before everything got started. After that, they started to do some disassembly of the locks after everything was cataloged. It was interesting to see that there was quite a bit of after the market repairs. You can see these really narrow stones right here. These are what we would typically refer to as Dutchman stones, or an after the fact repair that was just on the surface. And then that compares to some of these deeper tie stones that we see that go full through the wall. All of these were mortared together, so it took some time to take apart, cataloging all those face stones as they went. Gradually we got down to, this is the breast wall right here that goes to the lower lock chamber, and this would have been the top of the level that goes over to lock number 4. This is actually where we started to see the internal filling ports become pronounced here. So you can see that drop would come right over here. The water would go internal to the filling ports and then come out the sides over here. So as we went, you could see that it really was some pretty great stone masonry work that they did on these internal filling ports with the curves and how smooth it was and everything. And they just kept working that down. And a unique thing we found as we took from the breast wall, this would have been the top or the upper level of the lock chamber, down through the breast wall, we found one of these interesting timber frames. And our best guess was that this was some kind of ground improvement that they were trying to do to minimize settlement. So here's just some other photos of the internal filling port that we found as they went down. This is looking at it from inside the lock, and this is looking at it upstream of the lock. All that was documented in as-built and retained for our archives, and so we better know how those locks were created. One of the interesting things that we found at the bottom of the lock was, like I said, lock number 3 was set on timbers. These were actually the timbers that were underneath the lock wall. And we found that they were a mix of hardwoods and softwoods. It was oaks and pines. And typically, some of these were bad, obviously, because they were contributing to the movement or instability of the lock walls. But there were a few, quite a few, that were still in pretty good condition, considering that they were 187 years old since their original installation. And the hypothesis was that this was due to the fact that a lot of these timbers underneath the locks were under what we would call anaerobic conditions, or they weren't subjected to the air or oxidation or anything like that. But we found that once they were removed, they then weathered very quickly. They made up for lost time. So these were actually the timbers that were underneath the locks, and then these were some of the plankings that would run kind of parallel to the lock walls and the lock throat. So another interesting thing that we found in lock 3 was that as we disassembled it, we had some frame of reference from some other locks that we had on documented, some historic documents that we figured, there was wood underneath it, and that's what we found. And then we knew that the backs of the walls were staircased like big gravity walls. And the historic documentation we had on hand seemed to think that those would be about 7 feet thick at the very bottom. And that's what we showed in the design plans with the intent to field verify. Whenever we went to disassemble, we went down to the bottom, we found, oh, it's not 7 feet here. It's actually 8.5 feet on the one side and 8 feet on the other side. So that was a lot of good data. So now we know whenever we're looking at other locks, the typical heel thickness of that gravity wall. So now that we've finished full disassembly, gotten the wooden timbers out of the way, we then moved on to the rebuild phase. So instead of putting timbers back in, we went with a modern concrete slab. And so we put the reinforcing in, poured the concrete, and everywhere that the concrete was going to be exposed in the middle, we actually stamped and stained it to look like the planking that would have been there back in the operational day. So the end state really looked like this and this. Put all the stones back into place, finished up all the hardscapes, put in the lock gates, and it ended up being the finished product. The next project I'm going to tell you about is, again, one of those that kind of centers around another one of our interpretive boat programs. It's up in Great Falls, about 14 miles upstream of Washington, D.C. This is just some pictures showing Lock 20 and the boat going through there. And a lot of you folks that are really familiar with canals know that, whenever you go to work on a project, you're not just looking at just that one location as a solitaire or an isolated location. It's really part of a system, right? And what I'm showing you here is really the system diagram of the lower 23 miles of what we use to regulate water flow in the Chesapeake and Ohio Canal National Historical Park. I don't expect you to be able to see it. It's very small, but just to kind of recognize that it is a system. It needs to work as a system to regulate the flow in each of the reaches. And that's really what a lot of the aspects of this project were focused on. We did this work from 2017 over to 2020. And the intent was really to improve several locks, waste weirs, bridges, other water control structures to increase resiliency during the flooding and preserve the historic structures. Altogether, it was about $8.5 million, and it was spread over these locks 5 to 22. So we had a lot of different work areas spread about that, did different things. One of them was just as simple as replacing an ailing water control structure down at lock number 7. And, we just modernized it, made it a lot easier to operate and control the water level. And then we also included a flood resiliency feature, which is called a fuse plug spillway, a couple hundred feet downstream from this picture. And I'll tell you what a fuse plug spillway is in a few slides more in depthly. Another one that we did as part of this project was we have a whole bunch of dry laid stone walls throughout the park. This is at the Rock Run Culvert. And this one was actually constructed in 1829 to 1831. And there's a history of collapse in 1847. It was rebuilt, and the buttresses were added in 1848. And then it's just a lot of history that happens with this structure that signifies there's been some problems. This was the before picture, and this was the after picture. We also included a canal liner system to make it watertight. And interestingly enough, we see a lot of the signs of distress in these dry laid stone walls kind of become pronounced as either a localized bulge, or we see some of these larger sliding failures. And generally it's about 1/3 from the bottom of the wall that we'll see those planes kind of emerge as those stones just globally come out of the wall like that. So this is a before and an after. And you can see the buttress is still there, but that displacement happens in between the buttresses. So as we were disassembling this wall, it's always a real treat to see, what does the wall look like behind there. So this is actually a disassembly picture, and you can see kind of the shape of the wall coming down. Um, and I do a lot of strange reading at night, and I was reading a memoir about the stability of revetments and of their foundations that was from 1843, and it referenced the general rule of thumb from a 1716 report that said that the base width of the wall, or a dry laid stone wall, is about 1/3 of the wall's height. So in this case, this is a design drawing. We thought it may be as big as 15 feet, but as we took it down, we found that it was about 3 foot thick at the top, and then 4 foot, and then 6 foot, and then 8 feet at the bottom. So it ends up being about 42% of the height, which isn't too far from 1/3 of the height of the wall, which was in that rule of thumb from a 1716 report. But interestingly enough, the buttresses agreed with all the historic documentation. They weren't connected to it. They were kind of after the fact placement of it to try to increase the stability back in the day. So we tied our wall in behind it and made it a seamless transition. Some of the other things that we addressed in this project, this just shows one of these historic culverts that we have, one of the 168 plus culverts. These were all historic stone masonry. Many times we have a leak that initiates in the canal system. And then we get this cascading coming into the culvert that then leads usually to a sinkhole forming. And then in some cases, the interim measure is just to put some cofferdams on either end of the sinkhole in the culvert and the canal and put some bypass pipes. So in this case, we removed all that. We repaired the pipe. We remediated the sinkhole, put in a geopolymer liner, covered it with topsoil, seeded it, and made it back to an open canal. And of course, this project has the word locks in the title of it. We did do a lot of lock work. So this just shows one of the lessons learned that we had out there was that typically, no matter how close you look at these historic structures, you will end up finding new things during construction. And in this case, once we had a chance to lower the water, remove the sediment from this radius wall at the side of the lock, the instability in this whole radius wall became apparent, and in fact started moving out on us. We ended up having to rebuild it, which led to another discovery, which was that they had actually had problems with the instability of this radius wall historically. And we found what looks to be, I'd call it a historic rendition of a pile foundation that was made out of masonry that went all the way down to bedrock. So we incorporate that into the final design and rebuild. Some of the more simple repairs that we did that still have a big difference is repairing revetment systems that it would actually provide erosion resilience during upcoming floods. And then we also did some retaining wall repairs or replacements. And in some cases, like in the case of this one, we actually do some of these repairs with reinforced concrete in the back and a stone facade on the front. So there's the before and after. And then, everybody's canal is different. At the C&O Canal, everything's driven by the 1820s era technology. So as the water comes down and fills, the level in front of the lock or upstream of the lock, the excess water just goes around via gravity in these bypass flumes. So we did rebuild some of the bypass flumes, also put some lock gates in, repaired a whole lot of masonry, and put in some new bridges. The second to last component of this project was that we did rebuild waste weirs. So these are our type of water control structures. It's as simple as some paddle gates on the bottom and some weir boards on the top, and then the water flows through gravity through it and out to the river. This one in particular was taken down completely to the bedrock foundation and put back in a similar manner to match the character of the previous. And then this last one really showcases what the fuse plug spillway is. So all of our canals are subjected to overflow and flooding. In our case, the Sino Canal runs parallel to the Potomac River for 184.5 miles. In this section of the canal, the water will overtop low portions of the canal, come into the canal, and then that departure from the river level and the canal gets a little worse. So it looks for places to escape and jump back out of the canal and go back to the river. So where these low spots are and we have historic, damage from overtopping, we actually excavate out, put in these fuse plug spillways, which are intended low spots. So whenever the water does overtop there, it'll downcut only to this elevation where we put this articulated concrete block mat, which is a non-eroding control structure. And then we cover all that back up so nobody notices it until it's needed for those flood times. So all that being said, I'll switch to another project. This one we just finished back in March of 2023. This one is on 2 areas of the canal where we use the slack water of the Potomac River to navigate the boats out onto the river, and then they run on the slack water out until they come back into the canal. So this one was about 0.9 miles long. We did extensive stone masonry repairs that included anything from a full roll repair to an in-place repair. I did a lot of tree removals, had to raise some of the stone walls to reduce the amount of overtopping that we're experiencing that would close the trail and make us put a detour in that goes all the way over on these county roads. And then we had to do a whole lot of earthwork to bring everything back together as well. This is what this area looked like back in the canal operational area. There wasn't any trees. The mules pulled the boats right along the open Potomac River. And all those slack waters are actually impounded by these structures. Dam number 4 in this case is the one that backs the water up on the big slack water portion of McMahon's Mill to Lock 42 project. But in the same manner, dam number 5, which is right here, does a similar thing. And typically, whenever people come out to see these structures, it looks like this with about 2 inches or more of water over the run of the river spillway. But every once in a while, every year, we get the water off so you can see the full magnificence of these stone historic masonry structures that retain the water and impound the reservoirs. And sometimes during floods, you can barely even tell that the run of the river portion is there just from the amount of flow that goes over there. So back to McMahon's Mill, this is the problem we were trying to fix, which was the constant closing of the trail, which would then scour out the trail. Also all the trees that were jacking all the historic stones. So we then moved into construction, started establishing some erosion control measures. We would then install temporary boat docks here, and then we would mobilize the large barges and tugboats. At one point, they had 5 different barges out there and 2 tugboats. They started with the arborists. They would come out and clear all the trees off. That would then clear the way for doing excavation from the barges. And then they would find either bedrock or a competent course of stone that remained in place, and then start building up from there. And oftentimes, that wasn't an easy chore because dewatering here was not possible because the shape of the channel went straight down to the deep parts of the river. So they did all the work in the wet. So they would have people in waders and wetsuits, and with the help of excavators, they would place the stones. And then as they got higher and drier, it became a lot easier to place those stones in the dry. So altogether, they placed, I think, over 7.7 million pounds of stone masonry for this project between 2021 and 2023. So once the walls were built, then we backfill with the free draining backfill behind the wall and wrap that in geotextile. And this would provide relief of any kind of water pressure behind the wall and also prevent the formation of any sinkholes. We would then topsoil seed it for erosion protection, install our gravel base for our roadway. And throughout the whole process, we were continually doing inspections on behalf of the government, just making sure we were getting what we required. And that morphs from a whole bunch of different things because you're trying to inspect a new wall that's built underwater. It's not the easiest. So we did things like building underwater periscopes, using GoPro underwater cameras. And then at the end there, we got really good. We actually purchased a remote controlled submarine that you can see right here with a 4K HD camera that we would use to inspect some of these walls and make sure that we're getting the best product. So from there, it's pretty easy. Put down the resurfacing for our towpath, which are our primary trail system. We checked out everything using the primary mode of transportation for many of our visitors, which is bicycles. And then you end up with this end product right here. I got some before and afters here. This is a before project picture after all the trees were cleared, but before any wall repairs were done. And then you compare that to the afters, and you can see kind of the drastic difference that we had out there that really stabilized a good bit of the trail. It made it more resilient to flooding and made it a sustainable project. Second to last project I'll show you guys is the Conococheague Aqueduct. And this was one of the 5th of the 11th aqueducts built by the C&O Canal. And aqueducts are water bridges, right? So this is the canal, and the boats would go across it. And this one in particular has quite a starry past of history of damage. And so since it was originally completed in 1834, there had been damage in the Civil War we read about in the 1860s, another one in 1887, and then of course probably the most famous and dramatic in 1920 when an entire canal boat came through the side of this aqueduct into the Conococheague Creek below. After the 1920 boat incident, they built back a wooden trunk that we see here, and that's really what we mimicked for our project. So this was a 2017 to 2019 project where we stabilized the aqueduct, we restored the canal prism and constructed a concrete liner that would facilitate the rewatering. Total cost was about $10 million. Here's that interpretive boat that we see here. This is a lot of that stainless steel reinforcing that we had installed for that liner system. So Duncan kind of showed it before, but here is the before picture, and here is the after picture. So you can see the extent of that. An interesting thing we found in this one was you can see that there's some different coursing of stone here, which we knew that was after the market or after the initial construction repair. And the interesting thing that we found, or the link that we found during construction, was that those small stones were located right here in the red. And then in the gold star, that's where we actually found this Whitworth bolt buried in the canal, had been fired. And that's Whitworth bolt is about 12 pounds, 11 ounces, 2.75-inch diameter. It was originally patented in 1855 in England, from what I understand, has a spiral form and an accuracy of up to 6 miles. So there are accounts of that type of projectile being imported from England during the Civil War, and even being used by a local battery that had fought battles at Antietam, Gettysburg, and other major engagements in the area. So this is the type of cannon that would have fired that. This is not something we found. This is something that's at an adjacent national park at Gettysburg, but we did find this. So it's kind of a cause and effect story. So some other really quick things that we found on this one was we had the south abutment, the south pier, the north pier, the north abutment. We did extensive repairs on these just to prevent any erosion or further structural instability from erupting from them. There's a lot of ice jams, different things like that, flooding, but we did get those foundations cleaned up. We documented everything, saw kind of the condition. We're happy that we were there considering the condition that we saw. And once everything was cleaned up, we formed it up, drilled some stainless steel reinforcing in there, and then we poured concrete and kind of locked it all in there to protect it. And really you can see some of the instability that's being driven by these foundation conditions as those stresses are translated upward into these top courses of the masonry. So altogether, it was a pretty good project to form everything up. The other thing I will kind of lesson learned on this one was we can see a lot of the stress in these historic structures whenever we do detailed repairs on them. In this case, we found that the whole aqueduct had sagged about 3.5 inches downward due to the stress that it exhibited over that long lifespan. And then we also saw that it actually expanded or moved or curved downstream about 15 inches laterally, just from all the water pressures and flooding and things like that. So this was right before we flooded the aqueduct. You can see we did the cast in place form liners with the integral color to mimic the limestone over on this side, and then we did the stamped and acid etched stain on this side to match those timber outriggers from the 1924 repair. And the last one I'll leave you with, in the event that you're ever in the area or find interest in tunnels and canals and things like that, is that this is one that's wrapping up right now. Paw slope stabilization. We had a big rock slide that looked like this. And from that, we invested about $10 million to remove the rock slide, stabilize the slopes, and get this thing back open for traffic, including doing rock scaling, rock bolting, pin netting, shear keys, drainage improvements, and improvements to the boardwalk. So if you ever want to see a 3,118 linear foot long tunnel that goes through a mountainside, here it is, out near Old Town, Maryland. This is the new boardwalk we did. These are some of the measures we did with the rock anchors that actually pinned everything together. This is really the finished product where we did a whole bunch of shear keys that are actually like little shelves that hold up these unstable rock masses above them. That was actually sculpted, shotcrete, and they sculpted it to look like the adjacent rock and then stained it as well to really make it blend in. So over here, you can barely even see some of these unless you're a trained person who's seen them and inspected them many times. But that's kind of the finished product there. So apologize, went a few minutes over, but hopefully you enjoyed the whirlwind tour of some of the engineering structures here on the Chesapeake and Ohio Canal.
WCC Online is brought to you by Inland Waterways International, better known as IWI, TICI, the International Committee for the Conservation of Industrial Heritage, and the Society for Industrial Archaeology.